Before we start on today's lesson, which is graphing logarithm functions, let's review a little bit. What does a logarithm mean? And we introduced the other bases last time. So if I have log base 2 of 16, what does that mean? Or what is our answer going to be? So remember, that answer to a logarithm is the exponent. So you're looking for what exponent or what power 2 has to go to get to 16. And that would be 4. Notice that both of these mean the same thing. 2 to the 4th equals 16 is equivalent to log base 16 equals 4. The first one is considered the logarithmic statement, and this is considered the exponential. So on some of your problems, you've had to take them from one form into the other. So what about if I had log base 3 of 1 over 27? What would I get as my answer? So remember, you're looking for the exponent. So remember some of your exponents. 3 to the 1st would be 3. 3 squared would be 9. 3 cubed would be 27. So how would I get 1 over 27? Well, that would be a -3. And remember why that is true. So let's write the exponential statement. The exponential statement would be 3 to the -3 equals 1 over 27. We also learned about what is called the change of base formula. It's how we could put any of these in our calculator if we were unsure. So let's look at how we would put each of those in the calculator using the change of base formula. Log base 2 of 16 could be placed in the calculator as log of 16 divided by log of 2. And this is one way you can test your answers. You should get a 4 back. So log base 3 of 1 over 27 could be put in the calculator as log of 1/27 divided by log of 3. Now what if it's one that doesn't come out even? So here we have log base 2 of 12, which isn't one we know really well. So let's think about the ones that are around it. Well, we know log base 2 of 4 was 2, because 2 squared is 4. Log base 2 of 8 is 3. And the next one we know really well would be log base 2 of 16. 2 to the 4th power is 16. So we know that log base 2 of 12 would have to be between 3 and 4. So we can make an estimate that would have to be somewhere in between, maybe like 3.5 or something like that. Well, to find the exact value, we can use what is called that change of base formula. That change of base formula, remember, we just reviewed it, would be the log of that argument divided by the log of your base. So log base 2 of 12 I could represent as log of 12 over log of 2. And then we could actually put that in the calculator. So if you do log of 12 divided by log of 2, we get 3.585, which is between 3 and 4, almost halfway between. Now this is going to come into play later using that change of base formula, but right now we really want to look at 2 to the x and log base 2 of x, thinking about their graphs. So let's review. In the exponentials, if we filled in our table, 2 to the -2 would be a fraction. It'd be 1 over 2 squared, which is 1/4. 2 to the negative 1 would be 1 over 2. 2 to the 0 power would be 1. 2 to the first power would be 2. 2 squared would be 4, and so forth. So on my graph, let's see if I can draw a straight line. Here's my y-axis. And here's going to be my x-axis. Let's do different colors. I'll do red for the exponential. When x is negative 2, we're at 0.4, which is about there. When x is negative 1, we're at 1/2. When x is 0, we're at 1. X is 1, we're at 2. X is 2, we're at 4. And even when x is 3, we'd be up at 8. Oops. And we get a graph that looks something like this. Now let's fill in log base 2 of x. Now remember how 2 to the x and log base 2 of x are related. They're inverses. So inverses, we're going to switch our x and y's. And we can do the same thing here for the table. X value of negative 2 and 1/4 was the y, so we're going to switch them. Switch your x and y. Switch your x and y. Switch your x and y. And switch your x and y. Let's see what happens on the graph. When x is 1/4, we're at negative 2 down, so down here. Whoops. Negative 1. When x is 1, we're at 0. When x is 2, we're at 1. And when x is 4, we're at 2. So we get this curve going the other way. They're both increasing, but the exponential is increasing much faster. This one's kind of leveling off a little bit. Now notice we have that line of symmetry that we've talked about before. Right in between them, we could draw in, if I could draw a straight line, a line of symmetry. And that's the line y equals x. A function and its inverse will always be symmetrical about that line. Let's see what else we know about this. What's the domain and range of our exponential? Well, it's going on forever, that direction, to the left and to the right. We can plug in negatives and positives just fine. So our domain is going to be all real numbers. But our range is not. As we get smaller in our x values, we're just getting smaller and smaller fractions. But there's something they're never ever going to reach. 0. So on my exponential, my domain is all real numbers, and my range are the y values greater than 0. Now, on the logarithmic function, let's think about the x values we have. Look at how the x values are on the logarithmic. We're only starting here and going off to the right. Whoops. So, for our domain of our logarithmic, it's all the x's that are greater than 0. But our range, we're getting both negatives and positives back. It's all real numbers. So notice that our domain and range switch between a function and its inverse. Now, notice these boundaries. Those are because we have asymptotes. So let's look back at the graph. On the exponential, we have this horizontal asymptote. The horizontal asymptote is the line y equals 0. It's a boundary line. Now on the logarithmic, we have a vertical asymptote. x equals 0. Notice again that they swap, x's and y's. This one was horizontal, this one is vertical. Everything swaps. So we could fill these in here as well. For the exponential, it was y equals 0. For the logarithmic, it's going to be x equals 0. Now, what happens with the transformations? Well, transformations work the same way with every function. When you multiply by something on the outside, you get a... If anyone answered that, it should have been vertical stretch. When you add or subtract to your x, it should move your graph left and right. The number on the end should move you up and down. Now, we already graphed the parent of this function, log base 2 of x, on the previous page. So let's copy that onto this grid here at the bottom. When x was 1, we were at 0. When x was 2, we were at 1. 4 gave me a 2. 8 would give me a 3, and I have that boundary of the y-axis. So here is that, what we call a parent graph. It's the simplest one without being moved. This is the function log base 2 of x. Now we're going to go through a series of transformations. This is similar to what's being asked of you on your embedded assessment. Go through each one individually. So the first transformation is 3 times log base 2 of x. Well, if we remember, that's a vertical stretch by 3. Literally, we're going to take each of the y values and multiply by 3. So if this one had a y value, let me get my pointer out. This one had a y value of 0. 0 times 3 is 0. This point had a y value of 1. If I multiply that by 3, I'm going to get 3. The next good point has a y value of 2. If I multiply that by 3, I'm up to 6. So it really is stretching it. But it hasn't shifted left or right or up or down. So it's not going to change my domain or range. This is just the stretch. Now, the next one still has the vertical stretch, which we've already done in the graph, but the next thing that's happening to our function is the x plus 4. So I hope somebody remembers which way that's going to move it. It's going to move our graph left 4. So take each of your points and move it left 4 steps. So here's a good point. If I go 4 steps to the left, I'm now here. Take the next good point, which is here, and if I count 4 steps to the left, I'll be here. The next good point was here on the x-axis. If I move 4 steps to the left, I'll be there. And what else would get moved 4 steps to the left? Hope somebody said a vertical asymptote would get shifted to the left as well. Our boundary gets shifted too. Notice that the shape is not different. It is just shifted to the left. So we now have a vertical asymptote at x equals -4. Remember, this one didn't have a horizontal asymptote. We don't have to worry about that. It's the vertical asymptote that gets shifted. Now the last one, we have the stretch, we have the movement left, so we're going to have the vertical stretch, which we've already shown on our graph. we have left 4, and the minus 2 at the end. That's going to move all our points down 2. So on your embedded, you're going to need to show this series of transformations, and that's how they word it. This is what we're talking about, showing the progress of how that graph got transformed. And I would, I believe, if I were you, on your embedded is really make that one dark so we know that's the final placement once it's got done with all of its movements. Now, a few people had asked in one of the other classes, how could I graph this on my calculator? Well, there is a way. So let's talk about how that can happen. How could I graph this function on my calculator? Well, let's start with that parent graph of log of 2 to the x, log base 2 of x. Let me get my pen smaller again. Well, remember that change of base formula? I could do log of x divided by log of 2. We could do the same thing here. Here's the logarithm. We could do the change of base on that. See the 3 in the front, log of, now the change of base says we're going to take the log of the argument, x plus 4, divided by the log of the base, and at the end, you're going to subtract 2. So that is a way you could put it in the calculator. Now this works on any calculator. Some calculators actually have a special feature. And if any of you actually know how to do that, feel welcome to show that your neighbors. For next class, we will be having a check for understanding. You should be able to give the inverse of each function. You should be able to simplify. Write a logarithmic statement for each exponential, or write an exponential from the logarithmic. You should be able to evaluate. I would do these without a calculator. You should understand the change of base formula. And you should be able to describe the transformations. For the check for understanding, that's all I'm going to ask for. Now, on your embedded, you are asked to graph it in a series of transformation graphs, which is similar to what we just did here.